Okay guys, this is second part 2 of the robotic class at San Diego State University, and we are talking about the now forward kinematics. Forward kinematics. Okay, so when you're dealing with the robotics, you have to consider that these are the basics, but you have to know very clearly. If you don't know them, you are done. So look at this, a 2 degree of freedom robot, guys. This is a 2 degree of freedom robot. So here's the end effector, that's right. And the length of is L1 and the length of is L2. And we are measuring the length angle with respect to the world coordinate system, theta 1. Like this, and theta 2. So theta 1 is with respect to the world coordinate system that we are naming like this. These are the definitions, basic definition robotics, guys. Here we go. Say O naught, X naught, and Y naught. Understand? So we name O naught, X naught, and Y naught as world coordinate system, or fixed sometimes coordinate system. That's right. CS. Okay, so the world coordinate system that we are abbreviating by world coordinate system, we are abbreviating by WCS. So in the robotics, the first and trivial steps that you have to do, there is no way, if you ignore these trivial steps, you are making a huge mistakes, in particular for high degree of freedom robot like the Baxter I have in my at my DSCL lab. Okay, then you are setting up coordinate system on the links. I'm gonna teach you later how, okay, but accept from me now, this is let me change the color. Here we go. This is for the link one. Here is x1 and the normal to this y1, and for the link 2, that is, you can say the end effector here is x2 and y2, and the z's, they are out of the page. Obviously it is based on the right hand rule. Okay, right, let me see if it is recording. Okay, and let me ignore this stupid sound. Okay guys, so simply when we are talking about the forward kinematics in dynamics and robotics systems, we know angles of robot here, links, angles of links, and we calculate the position. I'm going to put inside the bracket orientation, that I'm going to talk about this later. Orientation of and effector, guys. At the end of the day, even that you have a robotic manipulator, or you have a legged walking robot, you want to know where the end effector goes, guys. You want to know the motion of the end effector, because this end effector are going to pick up the objects and move it for you, not the links, right? So in summary, robotics is that we want to know how to design the angles of the links that give you desirable trajectory of the end effector, right? But this is not the case. I'm going to explain why. Because you as a robotic engineer, you have to know, the desired trajectory that you want to go, that the end effector must go, and then you have to calculate these angles that I'm going to teach you, that is the inverse kinematics. But in forward kinematics, assuming that we know the angles, and now we can calculate the position and say orientation of the end effector. Understand? So obviously from trigonometry, from the high school, it's very easy. See, here we go. We are finding the projection of the end effector like this, saying that I'm naming here as O1, as I'll teach you later, and the O2. That's right. So O0 x1 y0, O1 x1 y1, O2 x2 y2, and the z's are out of the page. Understand? So on this thing, you can say that obviously is x2 is equal to, look at here guys, so I want to show it here out of the page. Here's theta 2, here's theta 1, that's right. So x2 by trigonometry is this length. I'm going to say x1 plus this length, x2 respect to 1. That's right. That's right. This length. Understand? And here is 90 degree. These are trivial trigonometry, guys. Right? Theta 1, theta 2. But here is, look at here guys, here is how much? Obviously is theta 1. This angle is theta 1. So the total angle for this triangle is how much? Is theta 1 plus theta 2, right? These are very trivial. So x1 is going to be L1 and the L2. So x1 going to be how much? Is L1 cosine theta 1, right? Cosine theta 1. This right angle, triangle. So, and here is going to be L2 plus L2 cosine what? Which angle? This angle. Theta 1 plus theta 2. So you found the x of the end effector with respect to the world coordinate system. So the y2 gonna be what? This height plus this height. So I'd say y1, y2 with respect to 1. Right, so it's gonna be from this triangle gonna be L1 sine theta 1 and obviously plus L2 sine theta 1 plus theta 2. Here we go. Understand? I'm naming this as equation number 1 and equation number 2. Okay? Now, after I found the positions of the end effector with respect to the world coordinate system, this is super important, very super important topics that we name it orientation, guys. Orientation of, this is very important, guys. I'm gonna show you right now in my lab. I have a 7-degree of freedom Baxter robot. I'm gonna tell you why. Orientation of the and effector, okay, effector. Orientation simply means angle of the end effector in the space, guys. So let me show you. Okay, so if you go to my lab, my PhD student Alex Bernito, he has done a research based on NSF grant, that autonomous deep learning based obstacle path planning. So I'm going to show it to you. This is 7-degree of freedom, guys. Robot, you see, is 7 degrees of freedom. Okay, 7 independent motion of the links. So, but based on the deep learning, robot learns the orientation of this 3D object. Okay, so how much is rotated in the XY plane. So when I run it, you see that the end effector rotates to be aligned with the angle of deflected angle of this object. Okay, so when I'm talking about the orientation, means that the angle that the end effector must rotate on the space. Understand? Look at here, guys. See, this is now horizontal. See it here? Oh, now it's 31. It's rotating. That's right. So when I say rotation, means this. Okay, at the end of the day, guys, orientation of end effector and the orientation of the position of the end effector is important for me. So now through this, you see that. Stop it. Oh. You see that. So end effector follows the trajectory. That's right. Follows the trajectory. I know this trajectory. Okay. So that if I want the robot follow this trajectory, as you have seen, okay, and passing the obstacle, now I have to go and find the angles. So the name of that is the inverse kinematics. Understand? So that's why I'm telling you the inverse kinematics is more important than the forward kinematics. Okay. So here we go. So now let's go to the orientation, the basic definition of the orientation. Okay, guys. Let me put this here because it's warming up. When it warms up, it's gonna make it difficult. So angle. So if you remember from the high school, guys, if we had two vectors of the A and the B, and the angles between them was alpha, if you remember, we had the inner product or dot product of the angles. Remember, A and B is equal to the absolute value of the A or the magnitude of the A and cosine between them. Remember? Okay, now. So now I want to see this coordinate system attached to the end effector. If I plot it here, guys, look at here. This is your world coordinate system or fixed coordinate system. O0, X0, and the Y0. And if you look at this, guys, if you look at this X2 and Y2, I'm just putting here, guys, and they are normal together, that's right. X2 and the Y2. This angle is 90 degrees, obviously. That's right. But X2 here is how much? Based on whatever we had here, is theta 1 plus theta 2. That's right. So this is normal to this normal. So here gonna also be how much? Theta 1 plus. These are from trigonometry of the high school, guys. Okay. Now I can say I'm defining a new topic in the orientation topic of robotics. Directional cosines or cosines of x2, y2 means coordinate system attached to an effector with respect to, this is how I write, with respect to x0 and y0, the world coordinate system. Directional cosines or cosines of this. Okay. So let us find together, guys. Okay, so this is recording. Yep. Okay. So if you look at this here, guys, I can write in the inner product format. I say x2 dot x0. That's right. It's gonna be what means projection of x2 over x0 is how much? Cosine of theta 1 plus theta 2. Am I right? It's very easy, guys. It's gonna be cosine of theta 1 plus theta 2. Right? Got here, guys? Yes, this is the projection on this. and the same for y2. So I'm gonna say x2 on the y0 means the world coordinate system gonna be from trigonometry sine of theta 1 plus theta 2. Agree, everyone? Now if you do the same with the y2, okay, we do the same with the y2, you have to find the projection here and projection here. So y2 is gonna be sine of theta 1 to theta 2, but in the negative direction. That's right. So it's gonna be y2 over x0 gonna be minus sine of theta 1 plus theta 2, and cosine of this in the positive side. So y2 dot means the directional cosines. Why we say directional cosines? Because it comes from definition of, simply, if I want to make it simple, definition of inner product, these cosines. Okay. So, and the y0 gonna be cosine of, or cosines theta 1 plus theta 2. Understand? Yep. So if I want to summarize, we found by the forward kinematics, we found the positions of the end effector based on the angles. Now we want to find orientation metrics of the end effector, okay, with respect to world coordinate system. So this is how we write. This is conventional robotics. We say x2 dot x0, x2 projection over y0, y2 projection on x0, and the y2 projection on y0. So because we have it from here, so I'm saying after this, in this course, I'm showing cosine with C and sine with S for simplicity. Okay, only for simplicity. So you're gonna have cosine of theta 1 plus theta 2 and sine of theta 1 plus theta 2 and minus sine of theta 1 plus theta 2 and the cosine of theta 1 plus theta 2. Here we go. Understand? And this is the orientation metrics of these 2 degree of freedom robotic arm with respect to the world coordinate system. Understand, everyone? Okay. Okay, so I'm naming this as equation number 3. So previously we had, I don't know what's wrong with the previously we had equation number 1 and 2, and now we have equation number 3. Maybe there is a shortage in hard drive. Hold on, I fix it, guys. Okay, so equation number 3. So I'm the equations 1 to 3 are called forward kinematics equations. Now, as I showed you, we do care about the inverse Mathematics. Okay, inverse kinematics. But before going to inverse kinematics, I prefer to teach you how to make a simulation of a 2D graph freedom robot in Matlab first, based on exactly these equations, guys. Based on equation number 1 and 2. Okay, it's pretty easy, guys. Just bear with me. Okay, I'm just doing that. Let me pause it until it comes up. Okay, guys, after having the Matlab, we just have to create an M file. Okay, and students ask me, can I upload the M files? Obviously I can. I'm gonna do it regularly by the Blackboard. Okay, so remember that you can make a comment. You say that the x2 was L1 in cosine of theta 1. Remember, based on the notes that you have, plus, oh sorry guys, L2, for having that you can see here. In L1 in cosine of theta 1, that's right, and we had exactly this for the y of the end effector, that's right. So y2 is, all of them are sine. Here we go. You never have to do that, but this is starting that how to make a simulation of a simple robot, okay, based on the forward kinematics. So I'm saying the L1 is 0.3, okay, meter. L2 is, I don't know, 0.25 meter. Who knows? Then obviously if I say it x2 is this and x1 is this, and say theta 1 is equal to from 0.1 to 0.1 to 1. Why I say 1? Do I mean 1 degree? Am I stupid? No, I'm not. You have to talk about in the radian. 1 radian is almost how much? How much, guys? You tell me. Yeah, 1 radian is 57 degree. Okay, and theta 2 I'm putting from, I don't know, 0.3 to 0.1 to 1.3. okay, can I? Yes, I can, obviously. So why I do that? Because I wanted that I want that the vectors of the theta, they must have the same lengths. We cannot add them in the mathematical algebra or in the Matlab that they have different lengths. That's right. And it's very easy. Look at here, guys. If I say length of oh my god, length of θ1, and the same here if you say length of θ2, okay, and if we run them, oh I don't, I just want to get close. If we run them, and okay, and for I'm saving the forward kinematic kin, okay, forward kinematics. I'm gonna upload on the Blackboard. So oh, it's a typo here, guys. Length right. What's going on? Okay, I don't care. So see, the lengths of those are 11. Okay, you cannot add them the other things. So oh, this is typo here. Sine, and here is L1. I don't know why I have done that. Okay, and here is the same here. You have to be very careful of the typos that you have in the code. Okay, so see that they have the same length. So if I plot it, so figure 1, I want to say plot theta based on you know what, I'm gonna say x2, okay, and the blue, okay, and hold on, plot y2, or you can say, yeah, y2. Yeah, you know what, I'm gonna plot it towards each other, so x2 and y2 and the grid, okay, and the grid. So if I run it, oh, see, this is x of the end effector, the y of the end effector. So when x is increasing, its y is, guys, decreasing. See that? Understand? So here we go. Understand? So, or you can say x2 and hold on, and y2 in red. Let us see what we get. Okay. Oh, the both are y2. Okay. Here we go. The red one is the y of the end effector, and this is the x of the end effector. Understand? So, but I want to have a simulation. I want to run it from a bus. Okay, these are not enough for me. So what I'm gonna do, first of all, I'm gonna make it, when I'm uploading Blackboard, you can uncomment that. Okay. What I'm gonna do, I'm gonna say this. I have to make a for loop, guys. And you know how to make a comment. Control R makes the comment. I'm gonna say for theta 1 from point 1 to point, so from 0 to point 1 to 1, and this is 0. Okay. So theta 1, guys. So theta 2 gonna be 0.3 to 0.1 to 1.3, simply. Now I'm gonna say x2 and y2 is this, but now if you look at the things here, guys, look at here, guys, you know, you only also need the point of this, which is L1 cosine theta 1, that's right. You need point of this and point of this. You mean position of x1 and O1 and position of O2, because you are making simulation of that. So if I write it here, this is x2 and x1. So let me write it here, because I want that you understand it. So x1 means that the position of O1 is L1 cosine theta 1, and the y1 is L1 sine theta 1. This and this. That's right. So you have to put it in your code. So you're gonna say x1 is L1 cosine theta 1. That's right. And the y1 is L1 sine theta 1. You got it? Clear? So now for each one of these, you're gonna do that. So now what you're gonna do, you're gonna say figure 1. Okay, guys, here you have to understand this is for what kinematic simulation based. So if you want to plot this line O0 O1 in Matlab, let me teach you guys. If you want to plot that line before going to inverse kinematics, you have to do this: plot x of O0 semicolon x of O1. y of o naught semicolon y of o1. This is general plotting a line in Matlab. So for plotting this part guys, this part of the robot, you have to say plot based on the code. Plot x1 and so okay, x1 means what is the x of the coordinate system here? 0. So here you have to say 0 and the x underline 1 in the code. That's right. What's the y of the word coordinate system? 0 and the y 1. Understand? The same is for the second link of the robot. For this part, guys, this plot. Now x1 connecting to the x2 based on the code I developed, and the y1 connecting to the y2. Underline, these are underlines. Understand? This is the general command in Matlab. This is not robotics. Okay? So what you're gonna do, you're gonna say figure 1, plot exactly as I did, 0 x underline 1 and 0 y underline 1. Understand? I'm saying blue. Okay? And if I say and, okay, and if I say you have to make axis clear. Axis is from 0, minimum of the x, maximum of the x, minimum of the y, maximum of the y. Okay? If I run this, let me see how it looks like. See? The line is moving, guys. This is very good. So, and I'm gonna make it line width gonna be, I'm saying, I don't know, 2. I want to make it more visible. Got here, guys. Here we go. Understand? So now hold on what? Hold on for the second part. Hold on for this, as I did in the notes. That's right. Hold on. Okay, hold on. X1, we define X1 here, Y1, X1, and now what? X2, that's right. And the Y1, what? Y2. And I'm making a different, these kind of things. So what you get is this. Oh, what happened? X1, X2, Y1, Y2. So hold on. I'm sorry, guys. I had stupid things here. So it was a vector. So this is how we make mistake. Theta is theta 1 plus 0.3. That's right. Based on whatever I said here. That's right. Theta 1.3. Now, if you run this, guys, okay. Oh, where's the pulse? Okay. Sorry, guys. So if you run this, see, you're gonna have this. Now, you see that the two-link robot is moving. But the problem is that the name of this is the stick diagram or the time lapse, right? So we don't want to have it. So why that happens? Because of this hold on command. What you're gonna do after the final command of this, you have to say hold off. If you say that, you're gonna have this. See? Now the robot is moving. Understand? So this is very interesting, guys. Okay, now the robot is moving. So if I say, let me see, if I increase that minus 0.8 to minus 0.8, okay, I want to just increase that to see what's happening. I'm going to put it in to 10. I'm going to 0.3 again. Okay, so here we go. See, the robot is moving like this, guys. But the schedule here is not after this. Where is that mistake? Oh, here we go. Okay, look at here, guys. See? Now you have a 2D graph robot that is working based on the forward kinematics. Or you can say simply, for a counter of 1 to 100, okay, theta 1 is sine of that counter, oh yeah, and theta 2 is cosine of that counter. Let us see what's happening, guys. Here we go. Robot is crazy, it's working at the same time. That's right, because we are moving to sine and cosine. That's right. So now we can put 0.21. Let's see what we get. Here we go. This angle is really put 10. There we go. See, it's moving very slowly. Right. So now the take-home message is that you can use Matlab for making simulations and the movies of your tooling robot in Matlab. Is that clear? Here we go. So I'm going to upload it on the Blackboard. Okay, enough. So now let's go to, see, it's running still. So now let's go to, I'm closing this. Let's go to what? Here we go. Okay, let's go to inverse kinematics. In inverse kinematics, as I said, we have position of end effector, as we do have in the 99 cases. You as a control engineer, you have the desired trajectory. When they say desired trajectory, means that you have desired trajectory of the end effector. Now you have to design a controller to generate proper length angle that gives you such a desired trajectory of the end effector. Understand? So we have position of end effector, and then we need to calculate the length angles in every scale of time. So this is like an inverse of mathematics, right? So how? For the problem that we have here, we know that we derive this for the end effector, guys. Okay. Okay. We derive this, guys. X of end effector was x2, that's right, was what? Was L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Yes or no? And the y of e is for end effector is y2 is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Right? Now I'm taking the time derivative from the both sides, guys. So you have x dot means velocity in x direction of end effector is minus L1 theta dot 1 sine theta 1 minus L2 theta dot 1 plus theta dot 2 sine theta 1 plus theta 2. This is from algebra in high school. So velocity of end effector in y direction gonna be L1 theta dot 1 cosine theta 1 because tangent of sine is cosine plus L2 theta dot 1 plus theta dot 2 what cosine theta 1 plus theta 2. Now I'm defining, I'm suppose that I taught you and you have learned this vector as x what x of end effector and the y of end effector. So time derivative of the x gonna be what velocity x dot e y dot e end effector. Then I'm gonna define capital theta as theta 1 and the theta 2. So capital theta dot is, or math theta is theta dot 1 theta dot 2. Understand? So on the other hand, now by having these guys, by having these you can find the relation between these guys. X dot, which is this, is equal to, okay, this and theta dot. Look at here, guys. So from the first line gonna be theta dot 1. Theta dot 1 is how much? Find theta dot 1, this and this, minus L1 sine theta 1, right, minus L2 sine theta 1 plus theta 2. Yes or no? Now find theta 2. Theta 2 is here. Minus L2 sine theta 1 plus theta 2. Understand? Now the next line, let me take it out because maybe second line, you're gonna have L1 see, cosine, oh it's warming up, theta 1, L1 cosine theta 1, okay, plus L2 cosine theta 1 plus theta 2, and now L2 cosine theta 1 plus theta 2. Now what we did, we connected the velocity of the end effector to the angular velocity of the links, to the angular velocity of links, and this is velocity of end effector, velocity of end effector. How? Geometrically. Understand? So the name of this famous matrix that you're gonna deal with this in robotic course forever, even that you have become researcher of robotics, is Jacobian matrix. Jacobian matrix is very famous matrix, Jacobian matrix, that is connecting the angular velocity of the links to the velocity of the end effector. That's right. But in forward kinematics, we have these. We want to calculate this. That's right. We have these. We want to calculate this. We have angles and the angular velocities. We want to calculate this. So in the forward kinematics, we are using this relation. X dot is equal to, and the Jacobian matrix we are showing with J Jacobian. J theta dot. Why? Because we do have these and we do have this, so we want to calculate this. But in inverse kinematics, okay, we have the end effector positions and the velocities and these kind of things. We want to calculate the angles. So what we're gonna do, we're gonna multiply the both sides of this by the inverse of the Jacobian. So you're gonna have theta dot gonna be Jacobian inverse x dot, because we do have this, so we want to calculate this in the inverse kinematics, as you have seen in the Backstream Matlab website. So we do have the robot and the effector picking up the object, passing the obstacle, putting on the destination. So we want to design a controller that generates what? These for me. Okay? Understand? So, okay. So let me see. Yeah. So that's enough. We are continuing the Jacobian matrix for the next class. One singularities and this kind of things, and we are continuing. Okay.